Hello, I'm Lucas Kramer and I will be presenting my paper, Strategic Tree Rewriting in Attribute Grammars. The slides for this talk are available at z.umin.edu/strag if you would like to follow along. Term rewriting is a useful paradigm in language engineering for expressing incremental transformations on terms, for example, performing compile time optimizations to simplify expressions or to perform desugaring. This is done by specifying rewrite rules that match on particular subterms and replace them with new terms. When the order of application of rules makes a difference, this can be controlled by defining strategies in systems such as Stratego. However, term rewriting systems cannot express semantic analyses well, such as computing free variables or performing type checking. Attribute grammars are another paradigm used in building language tools that work by decorating syntax trees with synthesized and inherited attributes, passing information up and down the tree. Attribute grammars work well for implementing these analyses, which can make use of contextual information, such as an environment using inherited attributes. While higher order attributes can be used to implement complex transformations, doing so requires writing lots of boilerplate equations, including ones for reductions that are otherwise untouched. Because of these respective limitations, neither approach is great for transformations that depend on context, such as inline let bindings and expressions, which would involve an environment context containing the bindings. Also note that both analyses and transformations are important in implementing almost any given language, so we'd like to integrate these approaches well in a single tool. Our solution to this challenge is to perform rewriting on trees that are decorated with attributes rather than on undecorated terms. Thus, we call our approach tree rewriting to distinguish it from term rewriting. Attributes can then be used for what attribute grammars do best, while strategies and concisely defined rewrite rules can access attributes during the rewriting process. For example, let inlining could make use of an inherited attribute for the environment, which is accessed in a rule that replaces a variable with its defining expression. Tree rewriting can be implemented by translating rules and strategies into attributes that occur on decorated trees and generating the equations that propagate them. As an example, consider the problem of performing optimizations on a simple functional language. We have basic mathematical expressions for addition, subtraction, and negation, as well as let expressions containing a sequence of declarations. A potential program fragment in this language will be parsed into the abstract syntax shown below. There may also be constructs for function definition and application, but we aren't concerned with them for now. We can specify some attributes for this language, here using the silver attribute grammar system. The free_vars synthesized attribute passes a list of all free variables in an expression up the tree. On a let expression, this requires removing the identifiers that are bound in the let. The used_vars inherited attribute passes information back down the tree to inform a list of declarations what names might potentially have a use. On a let expression, this is the free variables from the body. The defs and env attributes here contain a mapping of variable names to their defining expressions, which may be useful in performing optimizations such as inline let bindings, which will be discussed more shortly. These contain maybe expressions, and not simply expressions, because some constructs in the language, like functions, which aren't shown here, may introduce variables without a corresponding expression. We also might not want to inline some let bindings, such as ones containing computations that are used in multiple places. We can naturally express some optimizations on this language as incremental rewrite rules. Here, rules 1 through 6 correspond to basic mathematical identities for statically evaluating expressions. Rule 7 performs an inlining optimization. Note that this rule depends on the environment. Our implementation of tree rewriting is in the form of strategy attributes. These are ordinary, higher-order synthesized attributes with an associated rewriting strategy. These strategies are built from rewrite rules and can be composed using several combinators. In the optimized strategy, less than star is sequence. It applies the left strategy and then the right one if the left succeeds. Less than plus is choice. It tries the left strategy and if it fails applies the right one. All, some, and one specify traversals. They succeed when their argument is successfully applied to all, some, or one children of the term. The optimized strategy here fits a common pattern of performing an innermost traversal, so a convenient syntax for this and other common utility strategies are provided as extensions. Innermost applied to optimized step would expand to the strategy expression shown here. One doesn't write equations for a strategy attribute directly. Instead, one uses a propagate statement to direct the generation of equations. This isn't implicit due to limitations imposed by our implementation of strategy attributes as a modular extension to Silver, and we also see propagate as somewhat analogous to deriving in Haskell, for example. Strategy attributes may be partial, which means they can possibly fail when evaluated, or total, meaning that they will always succeed. The type of a partial strategy attribute on expr is maybe expr, while the type of a total strategy attribute is just expr. Unless declared otherwise, strategy attributes are considered total by default. Synthesized and inherited attributes can be used in defining strategies simply by accessing them in rules. Terms newly created by a rule are automatically provided with the same inherited attributes as the original trees. Here, the inline step strategy implements the inlining rule shown earlier by looking up n from the environment. The other rule in this strategy eliminates unused and empty declarations with the aid of the usedVars inherited attribute, which tracks all variables in a declaration that are eventually referenced by the corresponding let expression body. Now consider how to define a strategy attribute optimize inline that drives the inlining process while performing the previously mentioned optimizations. The obvious approach is to use innermost, which makes use of the all traversal as seen earlier. For maximum efficiency, all applies its argument on all children in the same decorated tree, rather than incrementally rewriting each child and recomputing attribute values between each. In the productions for let and sequence, usedVars for the first child depends on the second child, and env for the second child depends on the first. So using innermost would pose a problem here because all could cause some optimizations to be skipped, for example failing to remove a let binding that is no longer referenced. Instead, one fix is to repeatedly perform the bottommost, leftmost possible optimization and redecorate the entire tree. While workable, that approach is rather inefficient as attributes are recomputed across much of the tree when only a small portion has actually been changed between each iteration. An alternative is to use congruence strategies. These only succeed for a particular production, applying a list of strategies to the corresponding subtrees. This version of optimize inline mirrors innermost, except that we have special cases for sequence and let. When we see one of these productions, we first optimize the left child, which can simplify some bindings and enable them to be inlined. Then optimize the right child using the new defs computed from the first child, which can remove some variable references. Then optimize the left child again using the new usedVars computed from the right child, and potentially eliminate some now unused bindings. One must exercise more care in defining tree rewriting strategies than with regular term rewriting, as this sort of attribute dependencies between children can introduce subtle bugs and performance problems. Next, I will discuss how strategy attributes are implemented. Recall that strategy attributes are really just regular higher order attributes carrying a new term or maybe term value. For propagate declarations, we wish to generate aspect productions and equations from the attribute strategy expressions for the productions of the listed non-terminals. The optimized step strategy attribute is partial, so its type is a maybe result. The rule in this strategy is translated as a pattern match, where only the cases relevant to each production are included. This can be seen in the add production, where the 3 rules that match on add are included, while the const production matches no rule patterns, and thus optimized step is translated as nothing. Sometimes the translation of a strategy expression requires the generation of additional helper strategy attributes. For example, a sequence evaluates its right operand on a different, newly constructed tree than the original strategy. This must be translated by accessing an attribute on the result from the left operand. Here the right operand of the first sequence operation in the optimized strategy is not a reference to a strategy attribute, so we lift it into one named optimize second. Note that optimize second automatically occurs on and is propagated for the same non-terminals as optimize. Translations of traversals, choice, and sequence depend on the totality of the involved strategies. Here optimize and optimize second are both total strategy attributes. On the add production, all applied to optimize is translated as calling the add production with the results of optimizing both children. The sequence is translated by decorating the resulting term with all inherited attributes that occur on expr, just the environment in this case, and evaluating the optimized second attribute on this tree. On const, the all applied to optimized strategy expression is equivalent to the identity strategy since there are no children, so optimized second can be evaluated on the current tree without any explicit redecoration. Optimized second contains a sequence of a partial strategy attribute optimized step and a total strategy attribute optimize. This can be translated by pattern matching on the result of optimized step. On const, optimized step and thus also the sequence are guaranteed to fail. Thus the choice is translated simply as its right operand. We implemented a number of interesting example applications using strategy attributes. One is the untyped lambda calculus, where we re-implemented an example from Stratego and Kiyama as a comparison. Another interesting demo is using attribute grammars to implement regex matching via Brzezowski derivatives, one step of which involves rewriting the regex to simplify it according to various identities. There are more details on these applications available in our paper. Other applications, which I will discuss next, are normalizing for loops, and within the implementation of strategy attributes to optimize strategy expressions. Strategy attributes can be useful in building language extensions. For example, loop normalization using strategy attributes is done in the ABC halide extension. This is an extension to C that enables programmers to write optimizing transformations on nested for loops, such as parallelizing, unrolling, or tiling. Before these transformations can be applied, loops must first be normalized to count from 0 and use the less than and plus plus increment operators. This is done using strategy attributes. One of the required rules can be seen here, replacing uses of the less than or equal to operator with less than. This rule uses C concrete syntax patterns and expressions, highlighted in orange. These are extensions to Silver that are translated into ordinary production patterns and applications. Another application is internally in the implementation of strategy attributes to perform production-specific optimizations on strategy expressions before their translation. This enabled a roughly 20% performance speedup. The generic step strategy attribute contains rules for production-independent algebraic simplifications on strategies, such as that the sequence of failure and anything else will fail, or a choice between a total strategy and anything else is equivalent to the first strategy. The prod step strategy contains rules that depend on the production. The rule shown here accesses an attribute matches frame that determines whether any of the rule list patterns will match the current production. This attribute depends on another inherited attribute, frame, which isn't shown here, containing contextual information such as the name and signature of the production on which the strategy expression is being translated. Note that it isn't safe to apply prod step in some places in a strategy expression, such as in the right operand of a sequence, as we don't know what production will result from the left operand. Instead, it is only safe to apply the generic step strategy here. This is controlled using congruences. In conclusion, we believe that strategy attributes provide a quite natural and compelling integration of strategic term rewriting systems and attribute grammars. The applications that we have presented will be less elegant if implemented using only one approach or the other. Strategy attributes are especially useful in modular language extensions using forwarding. With forwarding, extension productions specify an equivalent forward tree on which attributes should be computed, including ones introduced by independent extensions. For example, in the halide extension, loop normalization with strategy attributes would look through productions introduced by other extensions that forward into for loops and normalize them, while these loops would be missed using undecorated term rewriting. One area of future work is in automatically finding performance issues in strategies arising from repeated decoration, as was seen in the inlining example. This is more of an issue with tree rewriting than undecorated term rewriting, since retraversing a tree can cause attributes to be recomputed. We have observed similar issues with forwarding, which is essentially a limited form of rewriting, so a solution to this would be more generally applicable. There are other boilerplate patterns that often recur in attribute grammar specifications. We are investigating other types of automatically propagated attributes to address these. For example, monoid attributes collect a list of values, such as error messages, up the tree, or pairs of synthesized and inherited attributes that thread a value through a tree or are used to compare trees for equality. With that, thank you for your time, and I would like to invite you to stick around for the Q&A session.